Imagine building a music application that catalogs thousands of songs from hundreds of artists. With such a large amount of data, quickly retrieving information on specific artists or songs is essential for a good user experience. Suppose a user wants to find the artist for a particular song. One approach is to create a large array of song objects to store the song titles and artist names. Then, starting with the first element at index 0, look at each song object in the array until you find the song you're looking for. However, because the application contains thousands of songs, searching for the right song will take a long time, which could frustrate your end users. A better solution is a hash map, which rapidly locates items in large data collections and is much faster than searching an array. In this video, you will learn the basic concepts of the hash map type and the benefits of using it when you need to find information as quickly as possible. Before you learn about hash maps, it helps to understand the concept of an identifier, because they are fundamental to how hash maps efficiently store and retrieve data. An identifier is a string of characters or numbers that uniquely identifies a person, place, or thing. For example, when using social media, you have a username that is unique to only you. That username is an identifier. So what is a hash map exactly? A hash map is a collection of key value pairs. A key is a unique identifier of some kind, such as your username or national ID number. A value is the information associated with that identifier, such as your social media profile or personal information in a national database. How can a hash map be used in your music application? Each song in the music application has a key and a value. The key is the song's title, and the value is the artist's name for that song. Consider the song Satisfaction by the Rolling Stones. In this instance, Satisfaction is the key, and the Rolling Stones is the value. In other words, the song title is an identifier that can be used as a key, while the artist or band's name is the value. Now imagine if the application you're building contained 20,000 songs. There would be many songs and artists to keep track of, so you would need a hash map to retrieve a song's artist as fast as possible. To demonstrate this, let's create a Java application called SongMap with a main method that can be executed from the command line. Import the hash map type from the java.util package by typing import java.util.hashmap. Remember that because hashmap is a Java class, it uses camel case for its class name. The next step in the body of the main method is to create an instance of the hashmap type. To do this, create a variable called map of type hashmap with the new keyword and a hashmap no argument constructor. This line of code creates an instance of a hashmap. Once the hashmap instance is created, you can add song titles and artist names. To do this, use the put method, which requires two parameters, the key and the value. In this case, the song title is the key and the artist name is the value. The type used for the key and value are both string types, but they do not have to be. Keys and values can be different class types. Add a print statement to put the contents of the hash map. Finally, run the Java application so it will print out the contents of the hashmap instance, which should display the song titles and artists like this. Notice that an equal sign separates each key from its value, in this case the song title and its artist, and that a comma separates each key value pair. This is the default print format for the contents of the hashmap type. You may also notice that the order of the songs and artists in the hashmap is not the same as the order in which they were entered. That's because a hash map is not an ordered list like an array. The order in which you add items to a hash map does not affect their storage order, because hash maps are designed for quick value retrieval, not for maintaining an ordered list. The keys used in a hash map, in this case song titles, must be unique. Adding two songs with the same titles will result in the first artist's name being overwritten by the second. For example, if you add two songs titled LOVE as shown, the song LOVE with the artist Alvin and the Chipmunks will have the artist changed to Nat King Cole, because only one artist's name can be associated with a song title. In this example, the assumption is that song titles are only associated with the original artist, and that two different songs can never have the same title. In reality, the world is very different. Cover songs, where a song is a new recording by a musician other than the original, are common. However, for the purposes of our example, you are not considering cover songs. Let's go back to the example. After adding the song titles and their artist names to the hash map instance, it's easy and quick to look up a song's artist by its title and print it. Here, the output from the print line will be Nat King Cole. This is correct. The song, Love, is no longer associated with Alvin and the Chipmunks. The entry's artist is now Nat King Cole, because you set the Love key to the value of Nat King Cole after you put in the Love key with the value of Alvin and the Chipmunks. Hashmap instances are extremely fast at looking up values by their key. They use hash algorithms to convert the key into a value that can be indexed and quickly referenced inside the hash map. Every instance used as a key must provide its hashed key to the hash map. The built-in data types, such as java.lang.string and int, all have built-in hashcode value algorithms. It's also possible to create custom hash algorithms for the classes you create, which will be covered later in the course. In this video, you learned that a hash map stores values in key value pairs and ensures that keys are unique. A hash map is used to quickly and efficiently look up values by their keys. It is an excellent addition to your software development toolkit when dealing with large amounts of data. Imagine that the music application you're building needs to track thousands of songs. While you've mastered adding and retrieving key value pairs using a hash map, there's much more you can do with it to enhance your application. Let's explore how. In this video, you will learn about some of the basic operations in hash maps, including replacing values, checking for the existence of keys, getting the number of key value pairs, clearing the hash map, and checking if the hash map is empty. Let's return to the sample of songs and artists from earlier. Song titles such as Satisfaction and their corresponding artists such as the Rolling Stones are stored in the hash map. Remember that song titles are unique to each song, meaning they are an identifier that can be used as a key. The name of the artist or band is the value. To demonstrate some basic operations of hash maps, a Java application called SongMap imports the hash map type and then creates an instance of a hash map that uses string types for both the keys and the values. It then uses the put method to add a few song titles and artists to the hash map instance. This should be familiar to you from the previous video. If you run the SongMap application, the output will look like this. Inside the curly braces, each song title and its corresponding artist's name. This is the default format when printing a hash map. As you learned, if the put method adds a key value pair to an existing key, the hash map will update the value. Let's update the song title yesterday to a new artist. The replaced value is returned if the put method updates an existing value. Running the program produces the following output. Initially, the hash map contains the key yesterday with the value Ray Charles. When the put method updates the value to the Beatles, it returns the previous value Ray Charles. Now the map shows that the yesterday song title has the value of the Beatles. Returning the value previously mapped to a key can be useful when you are unsure what the original value was or need to do something with it, such as adding it to a different hash map or logging the update. If you use the put method with a key that isn't in the hash map, it will simply add it as a new key value pair and return null. The return value is null when the put value adds a new key value pair. So, if yesterday wasn't already in the hash map, a new entry would be added, and the put method would return null. Another method that behaves similarly to the put method is the replace method. Let's change the put method call with the replace method call and see what happens. Running the program with the replace method call results in the same output as when the put method call was used. The method returns the value, Ray Charles, and replaces it with the Beatles for the key yesterday. However, the replace method behaves differently from the put method if it's called with a key that doesn't already exist in HashMap. The following attempts to replace the value mapped to the LOVE song title with the artist Nat King Cole. Running the program results in the following output. In this case, the value returned is null because the key, LOVE, doesn't exist in the hash map. If the key doesn't already exist in the hash map, the replace method doesn't modify the hash map. The map has the same contents before and after the call for the replacement method. The replace method is useful when you do not want to add a new key value pair if the key isn't already in the hash map. It will only update a value if the key is already present. You can check for the presence of a key using the contains key method. The contains key method returns a Boolean value. To demonstrate, the program tests for a key you know is in the hash map and then checks for a key you know is not in the hash map. Running the program results in the following output: true for testing for jump, but false when testing for LOVE. Knowing the number of elements in a hash map is often helpful. For example, you could display the total number of songs in the music application to the user. The size method can provide this information. The size method returns an int value equal to the number of key value pairs in the hash map. The print statement displays the size. The clear method removes all the contents from the hash map. If you call the clear method and then print the contents of the hash map, you get empty curly braces, signaling that the hash map is empty. Finally, you can use the isEmpty method to test if the hash map contains any elements. If the hash map is empty, the method returns true. If it has at least one key value pair, it returns false. In this case, the output is true because you called the clear method and emptied the hash map before calling the isEmpty method. In summary, the hash map is a powerful key value collection that enables lightning-fast access to data using unique key identifiers. Beyond basic operations like adding and updating entries, it offers advanced features to conditionally replace entries, check key presence, count elements, clear all entries, and verify if the map is empty. As a staple tool for Java developers, mastering hash maps will significantly enhance your ability to build efficient and dynamic applications, such as developing a music application that can hold large datasets. When managing large datasets, the data structure you choose can make or break your application's efficiency. While hash map shines in certain situations, it's not always the top choice. In this video, you'll learn how to leverage HashMap by understanding its performance characteristics, common use cases, and trade-offs. A hash map is like a digital dictionary where you store data as key value pairs. You can quickly look up a value if you know its key. For instance, you might store student IDs as keys and their names as values. But if keys or identifiers aren't important, you might be better off using a standard array, array list, or linked list. When you put a key value pair into a hash map, Java uses a hash function to convert the key into an index in its internal array. This enables quick access later. When you call the get method, the hash map hashes the key and goes directly to the corresponding index in its array. The average time to find, insert, or remove a key value pair in a hash map is typically very fast, around 01. This means the time doesn't increase much as more key value pairs are added. However, if many keys hash the same index, operations can slow down, potentially to ON in the worst case, meaning the efficiency of the hash map could be affected by the number of stored pairs. This is rare, but the hash map can slow down when it happens. In order to know when to implement a hash map, you'll need to understand how it uses memory and storage. To operate efficiently, HashMap uses extra memory and stores data in an array. A hash map starts with a capacity of 16, meaning it can initially hold up to 16 key value pairs. Each time a hash map exceeds its current capacity, it automatically doubles in size, requiring additional memory and processing power. With every instance of exceeding the capacity, the size continues to increase. In short, as you add more key value pairs, the array may need to grow, and this resizing consumes additional memory and time. The efficiency in storage a hash map offers means it outperforms other collection types in certain scenarios. To better appreciate its advantages, consider a university's registration system. First, a hash map is ideal for caching frequently accessed data, such as storing student data for quick retrieval in a web application. It's useful for counting occurrences, like the number of students registered for each class, where class codes are keys and student counts are values. HashMap is ideal for tasks like looking up a student's data by student ID. You store IDs as keys and student data objects as values, making lookups very fast. You can group data based on a specific attribute, like grouping students by grade. Now that you know these common use cases, let's explore when a hash map is the best choice for your project. In general, a hash map is great for a number of tasks and project conditions. HashMap is excellent for frequent lookups. First, if you frequently search for data by identifier, such as a student ID, HashMap is an excellent choice due to its fast lookup time. When data volume changes frequently and unpredictably, HashMap handles it well because it resizes as needed. And lastly, HashMap works best when keys are well distributed, meaning only a few keys hash to the same array index. This is difficult to predict, but complex keys are less likely to collide. While HashMap is fast, it comes with trade-offs. Most critically, it uses more memory than other collection types. A hash map requires space for the underlying array and additional space to maintain efficiency as it grows. If memory usage is a concern, consider other data structures like ArrayList or linked list. When selecting a data structure, consider your application's needs and ask, how frequently will I need to search, insert, or delete data? Is minimizing memory usage a priority for this application? Do I need the data to be sorted or evenly distributed in memory? For example, choose a hash map for speed, especially when you need fast searches by identifier and quick insert and delete operations. But consider a tree map, array list, or linked list when sorting data or maintaining sequence, such as sorting students by last name. If conserving memory is important, a standard array, array list, or linked list might be better. It is important to understand that a hash map functions efficiently when the hash values of its keys are evenly distributed across its buckets. Larger and more complex keys tend to generate a wider range of hash values, which helps ensure a balanced distribution, reducing the chances of multiple keys being mapped to the same bucket, thus improving performance. A tree map is an option too for sorted data and keeps keys in order, but it is slower for basic operations. Java's hash map is a powerful tool for efficiently storing and retrieving key value pairs. In this video, you've learned how HashMap works, how well it performs, and when it's best to use. In summary, HashMap is ideal for caching, counting frequencies, and quick lookups. However, be mindful of its high memory usage and the potential for slowdowns due to hash collisions. By selecting the right data structure, you can leverage HashMap for efficient, high-performance solutions while managing trade-offs effectively. Picture this. You're developing a university class registration system. One problem that needs to be addressed is the waiting lists for full classes. In this scenario, you have to maintain the order in which students were added to the waiting list, but you also need to be able to find students quickly, regardless of their position on the waiting list. While a hash map is unordered, there is another Java class that you can use to achieve this, the linked hash map. In this video, you will understand what a linked hash map is and how it's used, specifically how it can maintain the order of entries while providing efficient access to data. Remember that when you iterate through a hash map, the order in which you add the entries and the order they enumerate are unrelated. Hash maps do not order their entries. A linked hash map, on the other hand, maintains the order in which the entries were added. For example, in the registration system, a linked hash map can maintain the order in which students are added to the waiting list. To better understand how the linked hash map provides ordered entries, you can develop an application that adds students to a linked hash map. Then, print out the entries and see if the enumerated order matches the order in which they were added. The first thing you need to do is import the linked hash map type into our program. Like the hash map, the linked hash map is a member of the Java util package. Next, you create a class with a main method as a framework for our example. Once you have accomplished that, you can create the linked hash map. The linked hash map will store students' ID numbers as the keys and their full names as the values. You can add several students to the linked hash map in the order they requested to be added to the waitlist. You can iterate through the linked hash map to see all the students and the order in which they were added to the linked hash map. To do this, add a new static method below the main method that will print out the contents of the linked hash map. You will use this output method frequently. The variable I shows each student's numerical position on the waiting list. The for each loops through each entry in the linked hash map, casting them into the map entry type. It then prints the student's position, ID, and name. Call this method right after you add all the entries to the linked hash map. When you run the application, The output demonstrates that the enumerated items are in the same order as they were added to the linked hash map. The result is that the order in which the entries were added is preserved, with the first entry added being the first one printed. An interesting feature of the linked hash map is that it maintains the position of a key even if you update it with a different value. For example, use the put method to update the value associated with the fourth entry from John Smith to Lydia Apple, as shown here. When you print out the linked hash map, the order is the same, but the name associated with the fourth entry has been changed to Lydia Apple. This default ordering of entries in the linked hash map is called insertion order and is useful when you need to maintain the order in which items were added. The linked hash map supports another ordering system called access order, which will be covered in a future video. The tree map, similar to the linked hash map, can maintain the natural order of a key, meaning that it keeps whatever order might have built into the key. With the tree map, you can also customize the ordering. The tree map will also be covered in a future video. To wrap up, we've seen how the linked hash map can be a powerful tool in our university class registration system, especially for managing waiting lists. By maintaining the insertion order, linked hash map ensures that students are processed in the exact order they join the waitlist, while allowing quick access to any student's information. This balance of order and efficiency is crucial for developing a seamless and effective registration system and any other application that requires maintaining ordered entries with quick access. The fast access offered by hash maps is invaluable for quick data retrieval. But what if they also kept entries in order? That would be useful for scenarios like processing tasks in the order they arrive, or maintaining the sequence of events, like a waiting list. In this video, you'll learn how to manage elements in a linked hash map, including adding, removing, and retrieving entries while preserving their insertion order. Unlike a hash map, where the order of entries is unpredictable, a linked hash map maintains the sequence in which items were added. This feature is crucial when order matters. But just like a hash map, the linked hash map supports essential methods like put, get, and remove. This gives developers efficient data handling with the added benefit of preserving entry order. Let's consider an example. In the waiting list scenario, put is used to add students to a waiting list, and get retrieves their details. The linked hash map also has special methods for retrieving the first and last entries. So, when a spot opens up on the waiting list, it's given to the first person on the list, identified using first entry. The output shows that the lucky student who made the first entry is John Wells. Similarly, last entry returns the last person added to the list. Once John Wells gets into the class, we can remove him from the waitlist using the remove method. The remove method then returns the value of the removed entry, confirming that the action was successful. Nice. Knowing who's first and last is just one possible action. But what about everyone else on the list? With a little code, you'll be able to see who's still on the waiting list. As you can see, John Wells has been removed from the waiting list, but now all the other names are visible too. The linked hash map includes the put first and put last methods, which allow you to place an entry at the beginning or end of the list. However, what may not be obvious is how these methods, along with put, affect existing key value pairs. If the key used in put first or put last doesn't already exist, the entry is simply added to the first or last position. Similarly, if put is used with a new key, the entry is added at the end, just like with put last. However, if put first, or put last are used with an existing key, the location of that key value pair will change, depending on the method used. For example, if you take an existing entry and add it again with put first, it not only updates the value, but also moves that entry to the first position. You can try this with the ID CS9857859, which was originally assigned to John Smith. The output shows that David Bean has replaced John Smith for that student ID and is now at the top of the list. The behaviour for put last is similar to the behaviour for put first, except the entry moves to the end of the list. The put method works a bit differently. If the key is already present, the value is updated, but the key's position remains unchanged. Let's try this with the key AB4453455, currently linked to David Winston in the third position. If we use push to assign Bob Schmidt to this key, it will update the value but keep the key in the third position. Now Bob Schmidt has replaced David Winston, but the key remains in the third position. Perfect. In this video, you've seen how linked map combines fast access with order preservation, and how key methods like put, get, remove, put first, and put last help you manage and maintain the sequence of your data efficiently. These basic yet crucial techniques equip you to handle complex data management tasks with confidence, ensuring your applications run smoothly and efficiently. Managing data efficiently is key, especially with large datasets. But what if you need to prioritize some key value pairs while discarding those used less often, like a university might in its registration system? In this video, you'll learn how to create an access order linked hash map, where entries are ordered by how often they're accessed, not when they were added. To better discuss the concept of access order, consider a university's registration system. Imagine a class called Student that tracks key details for each student. As students log in, the application loads their information using this class. Having quick access to the student's ID, name, and language helps the system serve the student better when inputting data or reviewing information. It would drain computational resources to keep 40,000 student objects in memory. To manage this, you can implement a custom linked hash map that maintains a limited number of student objects in memory. These objects are used throughout the registration process, accessed with the get method, and updated with the put method as students register and input data. As students log in, the custom linked hash map stores their student objects. When it reaches its maximum capacity, it makes room for new logins by dropping student objects that haven't been used for a while. This might happen, for example, if students walk away from the registration process or close the app without logging off, which happens a lot more than you think. To save resources, we want to keep only the most active student objects in our custom linked hash map. The rest can be stored in a database or on disk and retrieved as needed. This approach is known as the least recently used, or LRU, caching algorithm. In short, the linked hash map automatically removes the least recently used objects to keep only the most active ones in memory. It's a common strategy to reduce system resource loads, and linked hash map natively supports this algorithm. To use the LRU features of linked hash map, you must extend it and override the remove eldest entry method. This method returns false by default, so the least recently used entries are not removed when new objects are added. You can modify this behavior by creating a custom class that extends linked hash map. Notice that the access order map class extends linked hash map, adding a capacity variable, defining its constructor, and overriding the remove eldest entry method. The access order map constructor calls the linked hash map superconstructor, passing in the capacity parameter while keeping a copy of the value. It also passes a standard load factor, the default setting for balancing memory and performance, and true for the access order parameter. The access order boolean tells the linked hash map to move the most recently accessed student object to the last position, shifting all other student objects toward the first position. The overridden remove eldest entry method checks the map's current size against its capacity. If the size exceeds the capacity, it returns true, removing the first entry. If not, it returns false and nothing is removed. So if you print the contents of access order map after adding 4 student objects, you'll see their order matches the order in which they were added. As expected, Antonio Lopez was added last, so he is in the last position. John Wells, added first, is in the first position as the least recently used object. The order changes as soon as we do anything to the entries in the linked hash map. For example, if you call get on the third entry like this, and then print out the contents again. David Winston, who was in the third position, is now in the last position because it was the most recently used object. If adding a new entry causes the linked hash map to exceed its capacity, the least recently used object, which is in the first position, will be removed. To see this in action, write the following code to add a new student object and then print the linked hash map again. The entry with an ID of 1, John Wells, in the first position was removed as planned, and the new entry with an ID of 5, Alan Cornworth, was added at the end. Perfect. The order has shifted. The linked hash map now reflects the LRU caching algorithm. The most recently used objects are preserved at the end, while the least recently used are ready to be removed from the front. In this video, you've learned how an access order, linked hash map, prioritizes the most frequently used entries while automatically discarding the least used ones. By extending the linked hash map and overriding key methods, you can efficiently manage memory and performance, making this approach ideal for implementing caching mechanisms like LRU caches. Whether managing a registration system or large datasets, access order linked hash map ensures crucial data is always accessible. This maximizes the efficiency and performance of any application you're working on. Imagine a bustling university registration day, where thousands of new and returning students sign up for classes. Your task is to keep all their names in perfect alphabetical order for each subject, no matter the chaos. But here's the challenge. Students register randomly, not alphabetically. So, you need a way to ensure every new registration fits into place alphabetically. Enter the tree map, your tool for turning chaos into order. A tree map works much like a linked hash map, storing key value pairs. But unlike a linked hash map, a tree map automatically sorts these pairs. Your keys will be sorted alphabetically from A to Z if they are student names. Conversely, they'll be sorted from 0 to 9 if the keys are numbers. In other words, string-type keys are ordered alphabetically, while numbers are stored in ascending numerical order, because these are the natural orders of these kinds of key types. Let's explore this in action. You'll create an application that registers students, keeping their names and home countries alphabetically. Start by importing the tree map and map types. The map type is needed to print out the entries in the tree map. Next, create a framework for the application with a class and main method for executing the code. Now you can create an instance of the tree map and add several students and their addresses. Finally, print out the entries in the order provided by the tree map, using a static method called printTree. Now, if you run this application, the output will show the students listed alphabetically. Remember that without specifying it, the tree map automatically ordered entries by their key, the name, in ascending alphabetical order. Had the keys been numerical, integers, doubles, etc., the items would have been ordered in numerical ascending order. The Java API defines several temporal types, such as date and time, that support natural ordering. However, most of the Java types you will use, besides strings, numerical values, and temporal types, do not support natural ordering. To account for this, use a pluggable ordering object, called a comparator, for types that do not have a natural order in Java, including those you define yourself. A comparator is any class that implements the Java util comparator interface. This interface has more than 24 methods, but the compare method is what you will focus on now. To demonstrate, here is an implementation of the comparator interface that orders the students by their last names in ascending alphabetical order. The compare method takes two objects that should be compared and returns an integer, which can be a negative number, a 0, or a positive number. If the integer returned by the compare method is negative, the first parameter is less than the second object. For example, 1 is numerically less than 2, and B is alphabetically less than A. If the compare method returns 0, the two objects are somehow equal, 1 equals 1 and A equals A. If it returns a positive number, the first object is, somehow, greater than the second. For example, 3.2 is numerically greater than 3.0, and the word cat is alphabetically greater than bat. The last name comparator compares two objects by their last names. First, it casts the objects passed into the compare method to string types. Then it sends each string to a custom method called lastName. The lastName method simply looks for the last space in the string and returns everything that follows. The underlying assumption is that the space separates the first name from the last name, and everything that follows that space is the last name. It's not perfect, but it works for this example and demonstrates that you can customize your processing when implementing the comparator interface. After the last name method returns, you can use the last name string values and the string type's built-in natural ordering to determine whether the last name of the first key is less than, equal to, or greater than the second key. The compare_to method is built into the string type and does the same action as a comparator. It returns a negative number if the calling string appears alphabetically before the parameter string. It returns 0 if both strings are the same. It returns a positive number if the parameter string comes before the calling string alphabetically. Let's test this comparator in action. Create a new instance of the tree map, but this time pass in the last name comparator in the constructor. Next, add all the key value pairs in the same order you did for the first tree map. When the second tree map is enumerated and printed, the entries are printed alphabetically by last name, not in the natural order of the full name or the order in which they were added. Overall, the tree map provides tremendous advantages when ordering key value pairs, and you can take advantage of custom ordering by creating comparator objects. The tree map isn't just about keeping things in order, it's about putting you in control. You can tailor the sorting to your needs with the right compare method. Experiment with your comparator objects and see how custom ordering can simplify your coding challenges. Imagine effortlessly transforming messy data into neatly ordered structures. Take the plunge, start experimenting, and unlock the full potential of TreeMap. Picture yourself designing a reporting feature for a university's registration office. This tool must provide swift and precise access to student data. How would you ensure that the GPA scores are managed efficiently and accurately? Tree maps can be an ideal solution for such challenges that involve sorting and retrieving data based on keys. In this lesson, you will learn how to effectively navigate through the elements of a tree map, using methods like first key, last key, higher key, and lower key. First, a tree map stores key value pairs in a sorted order. This sorting is based on the key's natural ordering, or by a comparator provided at tree map creation time. The inherent ordering allows for efficient retrieval of elements based on their keys. To understand how this is useful in the real world, imagine you are creating a tree map that uses students' GPAs as keys and their names as values. For simplicity, assume no two students have the same GPA. The tree map does not have a comparator, so it will use the natural ordering of the keys, which in this case are double types. When you run the program, the output prints the students from the lowest GPA to the highest. Great. And the tree map automatically orders the key value pairs according to the natural ordering of the double type used as the key. Now imagine you just need to know which student has the lowest GPA. The first key method returns the first, in other words the lowest, key currently in the map. Because of natural ordering, this would also be the lowest GPA. Here, the first key method is used to access this lowest key value. The next line uses the get method to retrieve the value associated with that key, in this case, the student's name. The last two lines print out the results. If you know the types of the keys and the values, you can cast them to their proper types as you access them in the tree map. When the types of keys or values are not known or incorrectly cast in a tree map, it can limit how the map is used and may lead to runtime errors. Casting the types is not needed in this scenario, but it would be helpful in cases where you need to work more intensely with the keys and values rather than just printing them out. Another way to fetch the first key value pair is using the first entry method. This makes the code look more complicated because you have to deal with the map entry type, but it's also more convenient. The output is the same. We just use first entry instead of first key. Note that all methods here have a map entry counterpart for fetching both key and value. We'll use key methods, but map entry methods are also available. Now let's turn to another useful method, the last key method, which accesses the key with the highest value in the tree map. In terms of GPA scores, this method would access the highest GPA according to the natural ordering of the double values. Calling this method is straightforward. Using object allows the variable to hold any type of object, providing flexibility but requiring type checking and casting if you need to use the value in a type-specific way. The output includes the student with the highest GPA was successfully retrieved from the tree map. Perfect. To get more specific with our navigation, the higher key method returns the next higher key compared to the key passed in as a parameter. To do this, call the method using one of the existing keys and print the output. Notice that hierarchy method fetches the next hierarchy, 3.75, not just any hierarchy. The hierarchy method works with any parameter, not just existing keys, as long as the parameter is the same type as the keys in the tree map. For example, here we are searching for the next higher GPA above 3.6. In the output, the 3.6 GPA isn't an existing key in the tree map, but the hierarchy method used it to find a GPA that was the next higher GPA. Just as the higher key method finds the next higher key compared to the parameter, the lower key method finds the next lower key in the tree map compared to the parameter. If no higher key or lower key exists, the method returns null. This can be used with any parameter of the right type, not just existing keys. When you run the program, the result reveals that 3.5 is the next lower key below 3.6. There are other lower keys in the tree map, such as 3.25 and 3.0, but the next lower key is 3.5. Navigating a tree map is an essential skill for Java developers. The tree map class provides methods to efficiently traverse and manipulate elements based on their keys. Understanding methods like first key, last key, higher key, and lower key allows developers to leverage the tree map's sorted nature for efficient key-based operations. Skills for effectively managing and navigating datasets are valuable for solving real-world challenges, such as developing dynamic reporting features for university registration systems or any application requiring efficient data organization and retrieval. By mastering these methods, you'll ensure your Java applications and solutions are both performant and robust. Java developers use a variety of data structures, each offering unique performance characteristics and specific use cases. Among the most useful advanced data structures in Java, the tree map class stands out for its ability to maintain key value pairs in sorted order. In this lesson, you'll explore tree map's performance, learn how to handle common use cases, and discover when it's best to use tree map over other data structures, specifically hash maps. So, how exactly does a tree map organize its data so well? A tree map uses what's called a red-black tree approach to organize entries internally. In a tree map, each key value pair links to two other entries, one with a lower key and one with a higher key. This structure ensures the keys are maintained in sorted order, which is great for efficient data retrieval and maintaining sorted sequences. In the tree, the root is the entry with the key of 10. Keys lower in order are referenced on the left, and the higher keys are on the right. So, for example, 5 is found to the left of 10 because it's a lower value, and 15 is to the right because it's higher. When the entry with the 3 key is added, it's less than 10 and less than 5, so it falls to the left reference of the entry with the 5 key, and so on. This structure is great for ordering any set of keys naturally or by comparator. The tree map continuously works to keep the structure balanced, much like a well-architected pyramid. It aims to minimize the width and height of the tree, ensuring efficient data retrieval and maintaining sorted sequences. This maintenance impacts performance, as the operations of adding, removing, and finding elements all have a time complexity of O log n, where n is the number of elements in the tree map. This is because the tree map doesn't use an underlying array, like a hash map. Instead, it links all its entries together in a pyramid structure. This results in more complexity and more time is required to find, add, and remove key value pairs than with the hash map. Another key performance characteristic of a tree map relates to iteration. Iterating over the key or values is relatively fast with a tree map because the keys are maintained in sorted order. The tree map maintains extra data. Each entry links to two other entries to ensure the tree remains balanced in a pyramidal shape. This ordered structure facilitates efficient retrieval and is particularly useful for applications requiring ordered data processing, such as range queries and data navigation. However, note that while this memory overhead is generally not significant, it can be a consideration in memory-constrained environments. In terms of use cases for a tree map, two stand out: sort ordering and navigation. When the requirement is to maintain elements in a sorted order, tree map is the go-to choice. For example, an alphabetical list of students. The tree map also provides methods that make it easier to navigate among keys, including the methods first key, last key, lower key, and higher key. For example, finding the lowest or highest GPA among students at a university. Tree map and hash map are suited to different use cases, each offering unique advantages. Let's highlight the key differences to help you make informed decisions on which to use and when. First, the hash map is faster than a tree map because it uses an array internally and indexes entries according to the hash code of their keys. A tree map, on the other hand, links entries together, requiring more work and time to add, remove, and find entries. The hash map also uses less memory than a tree map because it maintains fewer objects than a tree map. While the differences are negligible with small datasets, they become more important with very large datasets. Crucially, the hash map does not maintain entries in any particular order. When you iterate through a hash map, you cannot predict in what order the key value pairs will be enumerated. A tree map maintains the natural order of the keys, or it can be initialized with a comparator to maintain a custom order. Finally, the navigation capabilities of a tree map are more sophisticated than a hash map. Both the hash map and tree map can fetch a value directly by its key and iterate through the entries, but the tree map can also access entries based on their relative sort order, such as the next highest key, something that the hash map cannot do. To wrap up, the tree map in Java is a powerful data structure that offers efficient sorted key value pair management. Its performance characteristics in adding, removing, and finding key value pairs make it suitable for various use cases where order and consistency are paramount. A tree map does have trade-offs in terms of memory usage and slightly slower operations compared to hash map. However, its ability to maintain order and provide more sophisticated navigation makes it indispensable in scenarios requiring sorted data. In short, choosing between tree map and hash map ultimately depends on your application's specific requirements. For sorted data, tree map is the better choice. For fast access and lower memory usage, hash map is preferable. By understanding these differences, Java developers can make better informed decisions about when to use advanced data structures. This ensures their applications perform optimally and meet the requirements for order and efficiency.